Let's just start by having a look at galvanic cells. When we talk about galvanic cells, we're talking about voltaic cells. These are cells where you'll notice that there is no external power source connected to the circuit, which means that the redox reactions that we will be looking at with galvanic cells will be spontaneous redox reactions. This is different from electrolytic cells where we had non-spontaneous redox reactions. So you'll see normally we will work with substances that are strong oxidizing and strong reducing agents, and therefore the reaction occurs spontaneously. Now the reactants are not in direct contact with one another. So when we have a galvanic cell, you'll see that there is one beaker where we will have our one anode or electrode and another beaker where we will have our cathode. And then there is a connection, an external circuit, normally a voltmeter connecting the two. And then between these two beakers, remember that there will be an electrolyte inside each beaker. There will be a connecting salt bridge. So let's go and investigate a specific example. This salt bridge connects the two electrolyte solutions with one another. If we go and we investigate a zinc-copper galvanic cell, we know that zinc and copper on our table of standard reduction potentials has certain values. So if you go and you have a look at it, you'll see that a Zn2 plus 2 electrons will form Zn, and I'm writing down the half reaction with the double arrows in the middle. It has a value of negative 0.76 volt. If we go and we look at copper, and now I'm talking about copper 2 plus 2 electrons, and I write down the double arrows, you will see that it will form Cu, and it has a value of plus 0.34 volt. So between these two, when I look at these values, I see that copper 2 plus is a stronger oxidizing agent than Zn2 plus, which means that copper will be the one that goes through the reduction. If you look at Zn2 plus 2 electrons, because of this negative value, we see that it has a lower reducing potential, which means that the Zn will go through oxidation. So now when I go and I write down my two half reactions here, this is what I'll have. I'll have Cu2 plus 2 electrons becoming Cu with a value of 0.34 volts positive, and I will have Zn becoming Zn2 plus 2 electrons. Remember, now I've already decided the directions, that's why I'm only using the single arrow, and because I have decided that this is my oxidation half reaction, I'm writing it from right to left. This becomes plus 0.76 volts. And as you can see, when we go and calculate the cell potential, it gives us a value of 0.34 plus 0.76, 1.1 volt. Now if we look at the setup of this galvanic cell, let's go and focus on our oxidation half cell. Very important that you pay attention, because there's a very big difference between galvanic cells and electrolytic cells. If this is the anode, we know that oxidation always occurs at the anode. The half reaction for oxidation is this zinc reaction. It means that this electrode will be made of zinc, and it will go through oxidation, and we will see the formation of Zn2 plus ions. If we look at our cathode, where reduction occurs, we then know that Cu2 plus must be in solution so that it will form Cu on this electrode. This electrode is made of copper, and a copper residue will form on it. It means that the copper cathode will increase in its mass, and remember, the zinc anode will decrease in its mass because it's going through oxidation. Now here's the tricky part. Have a look at this. You know that in the past, when we looked at the electrolytic cell, the anode was positive. Now I'm telling you that the anode is negative and the cathode is positive. And this causes the flow of electrons. Have a look at it. The flow of electrons will be in this direction, from the anode to the cathode. In the electrolytic cell, it was from the cathode to the anode. Now it's from the anode to the cathode. Very important here, the negative sign at the anode just indicates a change in direction that occurred here. So what happens here, and look at this very closely. At my anode, where I have Zn becoming Zn2+, those electrons that are released will travel via my external circuit all the way to my cathode. At my cathode, those electrons are going to combine with the Cu2+ in solution to form the copper residue on the cathode. That's a basic difference here. Number one difference between electrolytic cells and galvanic cells is the fact that a galvanic cell has no external power source. This voltmeter just shows me that there is potential, that there is current flowing, electrons are moving. And in the electrolytic cell, we have that power source. Another difference between the electrolytic cells and the galvanic cells is the fact that spontaneous redox reactions are used for galvanic cells, while for our electrolytic cells, we know that we use non-spontaneous redox reactions. The big difference here, the anode is now negative and the cathode positive. And remember, direction is indicated by the positive and the negative. So our electrons will flow from the anode to the cathode. Now I want to quickly talk to you about the salt bridge here in the middle, this section over here. If you look at this diagram, keep your eyes on the oxidation half cell on the left-hand side. And you see that the anode's negative. Now we see that zinc forming Zinc2+ can eventually lead to a buildup of positive ions in this half cell. But since it has to be negative for there to be a difference and to cause the flow of electrons, this buildup of Zinc2+ ions must be prevented. And that's why the salt bridge is here to connect the two half cells to one another. The Zn2+ cations will still flow to the cathode. And this will prevent the buildup of positive charges in our negative, around our negative electrode. So the Zn2+ must travel via the salt bridge. Also, when you look at the copper that you see, remember that there is a decrease over time of the positive charges at the oxidation, decrease over time of the positive charges here where reduction occurs. The Cu2+ becomes Cu. But remember, the cathode is positive. So because we see our positive charges decreasing, we also need it to be more positive. So the transfer of the cations to the cathode prevents a shortcut here, prevents the circuit from stopping. The flow of current is going to continue. Our cations still travel to our cathode, and similarly our anions can still travel to our anode. Also inside your salt bridge, there will be an electrolyte solution, and this electrolyte solution is normally made of a very weak oxidizing reducing agent. So the reason why we use a weak oxidizing and reducing agent here is because we don't want it to participate in oxidation reduction at our half cells. So the salt bridge itself is actually filled with this electrolyte. It's plugged with cotton wool on each end, and remember that the ions inside will be weak oxidizing and reducing agents, basically spectator ions that will not participate in the reaction.